I'm happy to introduce Karine Chemla, who is a CNRS researcher and currently affiliated with the University of Edinburgh and the Labosphere at Paris Cité. So I want to keep my introduction very, very short, so I will not go through all of Karine's achievements. It would take us an hour. But the only achievement I did want to mention today is that she was recently elected to the French Academy of Sciences, which is, I think, a huge achievement, especially for someone coming from the humanities. So now let us turn to the topic at hand. So Karine's talk is the opening talk of the literacy event, and Michael and myself are organizing here. So I'm confident that with Karine's talk, we will immediately get to the topic, but for the historians of computing here, perhaps from a slightly surprising angle, because she will speak about types of literacy to be able to historically differentiate between different computational and mathematical practices in ancient Chinese mathematics. So Karine, you have the floor.
Thank you so much, Lisbeth, and thank you, Michael, for the invitation to share ideas with you. It's a real pleasure to be with all of us. And what I would like to do today is to return my 2009 paper on literacy, offering for it additions that were, at the time when I wrote this paper, out of reach for me. But to begin with, I need to give you a very rough idea of the kind of mathematical documents from early imperial China that are available to historians. And I'm going to limit myself to until roughly the 10th century for reasons that I will come here in a moment. So in fact, we have two major types of sources Chinese. The first one is the documents that were handed down through the written tradition, such as this one. This is a printed edition from the 13th century of a canon that was composed in the first century of the Common Era. And these kind of documents were, until the 20th century, the only available to modern historians to work on the history of Westerners. Here is roughly a list of these documents. I will return to this slide shortly. These are 10 canonical texts, one of which I have first out is in fact lost. And in addition to this, we have a related book related in ways to which I return. So these were the texts that were handed down through the written tradition. And I have highlighted in blue two of them, the oldest ones, in order to give you an impression that all of these texts were written after the first century. This is the time for me of the completion of these two documents, even though naturally they may contain parts that were older. If you're interested in this, we can return to this point in the discussion. So the first corpus, let us say, between the first century of the Common Era and the 8th century, in fact, of the Common Era. And these works, the 9 chapters, most of the other canonical texts, these works were composed of problems and procedures. Procedures, in modern terms, algorithms, are going to be the focus of my lecture today. Not exactly all of the works I've shown are of this type, but I'm not going to enter into these details now. So much for the first kind of document. But since the end of the 20th century, documents have been yielded by archaeological excavations, all kinds of excavation. You can see one of them. These documents were buried in tombs or unfortunately looted and can be bought on the antiquities market. Here is a list of those documents that were published for the first ones and not yet published for the last one. Basically, what we have with these documents are documents that come to us directly from the hands of those who use them. That's the first point. And they are documents that were found in environments that archaeologists date to the 3rd or the 2nd century before the Common Era. So basically, we have a set of documents that is much older than the other documents I've started with, those that were handed down through the written tradition.
Karine, can you go back to the slide with the image on it? Can you say a bit more about that as an artifact? I mean, how big is it?
This one?
Yeah.
I think that the slips are like this, more or less. So they were written on bamboo slips. The bamboo slips were connected by cords that decayed in the tomb. So when archaeologists find documents of this kind, they find basically a bundle of slips, and they have to find again the order in which the slips were used by the user. If you're interested, I can give you some references to read more, or we can talk about it later if you're interested. So, from these mathematical manuscripts, I'm going to evoke only two, and mainly the first one, writings on mathematical procedures that was found in a tomb, sealed in or shortly after 186 before the Common Era. And again, in these documents, we have mainly problems, procedures, and tables. I have not highlighted tables very much in the previous slide. We have some tables in the canonical text, but in this text, we have many more numerical tables. And hence, from the viewpoint of the content, we have a certain type of continuity between these early manuscripts and the canonical texts. There is a second element of continuity, which is this. Both the canonical text handed down and the manuscripts to which I have referred, because they were found in terms of books on the antiquities market, both refer to placing numbers somewhere out of the text. Both refer to swan, which I translate as calculating words. They were put, these words, on the surface, about which nothing is known. This is part of what I will call the computing technology, even though I will explain why I consider this is only part of the computing technology. However, what you see is what we have, namely, even though they refer to words, even though they refer to placing numbers somewhere, these manuscripts, these documents handed down, only contain Chinese characters. And in particular, they never illustrate what is done, what was done with calculating words. So we have here a second type of continuity between the documents handed down and the manuscripts, which confronts us with a problem on which I often insist. In order to study the computing technology, we must restore what happened outside the text. And so we can only rely on clues, and hence this is a huge methodological problem. And this is all the more big methodological problem that I'm going to focus on precisely what happened outside the text. Here is the thesis that I would like to define for you today. I would like to argue that between the time of the early manuscript, so the 2nd, 3rd century before the Common Era, and the time of the canonical text, starting in my view from the 1st century of the Common Era, there was a mutation in the use of the calculative roles. There was a new use of the roles, which, in my view, can be interpreted as a change of technology, because the technology must be considered in relation to the use to be complete, as I hope to make clear. And I would like to argue that in relation to this mutation in the use of calculative works, there was a mutation in mathematical practice and knowledge. I would like to show a key change in both practice and knowledge. And I will focus, for reasons that will become clear, on a topic that is central to this, which is the execution of division and the reflection on division, because it will be a key piece of knowledge on which we can observe this mutation. So, as I explained, to argue for this thesis, my method must rely on clues, since nothing in the sources shows the calculating rods at the time, or even describes what was done with them, except with clues. So, the first important methodological point to consider is why the canonical texts were handed down through the written tradition. Because this question will give us a major clue on the division that was associated with the canonical texts. And this is where I return to the sources handed down through the written tradition to show that these texts were kept because of the very specific history in which they became major protagonists. Indeed, in the 7th century, something essential happened. Upon imperial order, Li Chongfang and colleagues, we had a team working under his supervision, prepared an edition of the 10 canonical texts, those whose list I projected, which involved seeking for commentaries that were important, which involved editing the text, which involved writing sub-commentaries on the ancient texts and the commentaries and so on. And they presented the result to the throne in 656. This was part of a broader cultural movement that bore on the canonical text in many different domains of scholarship. Mathematics was one of them. So the key fact is that these 10 classical texts of mathematics, these 10 canonical texts of mathematics, immediately after became textbooks in the School of Mathematics of the Imperial University. So a School of Mathematics was established, at the end of which students could take exams, and passing the exam would enable them to get a position in the bureaucracy. What happened in the 7th century is essential exactly from this perspective, because in later centuries there were recurring attempts to re-establish a school of mathematics And in relation to the re-establishment of the School of Mathematics and the re-establishment of examinations, the 10 classics that had been used for teaching, as well as an auxiliary book whose title is at the bottom of the slide, were reprinted. This is what is behind the 13th century printed edition that I have projected at the beginning of the talk. So this corpus of texts that were handed down through the written tradition, these are the only ones that have survived through the written tradition, and we can interpret the fact that they have survived thanks to the fact that they were printed and reprinted in relation to the re-establishment of the School of Mathematics and in particular of examinations to select the students.
Karine,
Yes,
is that Suan the same as the calculating rod? or
exactly,
It is.
exactly the same. Thank you for the remark. Yes, we can discuss about some later. Thank you. So some of my colleagues, notably Alexei Volkov, have worked on the education that was given in the School of Mathematics, and they have established, and this is where I return to my slides listing the 10 canons, that in this school, there were two curricula, the top one teaching the first 8 texts, and the advanced curriculum in which the students studied the last 2 texts, the remaining text, the one that was at the bottom of my slide, being taught in both curricula. And you can have a look at the chronology of the text and the order in which they were taught. They were not taught in chronological order, but the first canonical text taught was a text that had been composed according to Thienbarson around 400 of the common era. And this will be an essential clue for what follows. So what I claim is that the fact that these 10 books were taught together implies that basically they were part of the same mathematical culture, that they embodied the mathematical culture that was taught at the School of Mathematics. And this will give a key clue to the use of the calculating rods in relation to these canonical texts. So in what follows, I will focus on the elementary curriculum, and I will begin by the mathematical canon by Master Sun, because in this text we have key elements of the basic literacy and key elements of the basic literacy that, in my view, were valid for all canonical texts. There are details to be discussed, but I don't have now the time to discuss these details. So it's really important to understand that if we studied these works separately, we would perceive that there are elements that are missing, that there is tacit knowledge that should have been given orally or whatever. But if one looks at the set of books that were used together, then we have elements at the beginning of the curriculum that sheds light on pieces of knowledge with which other books were taught. So I make the assumption that the elements that are taught at the beginning hold true for all the canon in the curriculum, with exceptions that I'm ready to discuss. And without entering into the details, several clues confirm this assumption. So we will begin to have a look at the teaching of the numeration system and of computing technology. So this is what we have at the beginning of mathematical canon by Master Sun, which is the first text taught in the elementary curriculum. We have measurement units, names of large numbers and relationship between them, approximate numbers for circumference, diameter of the circle, side diagonal of the sphere, and so on. And then we have what I translate as a universal method to compute with calculating words. And here we have the description of the way of writing numbers according to the place value decimal system. And I would like to teach you through this text. So to begin with, you see the use in the first sentence of the term position. Position is the term that is going to be central in my talk. For any method using calculating words, one first determines the corresponding positions. Position is not easy to interpret here, and we will return to the interpretation of this term recurrently. So I have translated the text, but I would like to have you read the text in relation to another much later manuscript that was found at Dunhuang in Central Asia, a manuscript in which, for the first time, in addition to Chinese characters that we find in all the columns, at the bottom of each column, we have the illustration of calculating words and how they were used. And what I would like to show you very briefly is how the description given in the mathematical canon by Master Sun, how this description fits with what we see here. So I have translated the numbers that appear below in so-called Arabic numerals on top to help you. And because I consider this system to be place value, I have used this system. You will see later someone else have done. So you have here anyhow one of the earliest extant testimonies of the illustration of the use of calculating rows, to which earlier texts only referred without showing. So when the text says the ones correspond to vertical, you can see here that you have under 32, you have the vertical 2, the vertical 4, and the 24. So you can see in which respect the ones correspond to vertical. The tens to horizontal, you have the 20 of 24 here, the 30 of 32 here. So you have an alternation between vertical, horizontal, and then the hundreds erected, the thousand declining. So you have an alternation between vertical, horizontal. Yes?
When you look at the 9, those 4, are those also horizontal ones, or how does it?
Excellent question. So if you see 4 horizontal, how do you interpret?
I think it's 4 plus 5.
In fact, oh, sorry.
But
I'm sorry. So you speak of this.
no,
What?
on the right, the 9.
Here? Okay, this is the next one. I thought you were speaking of this.
Ah,
And this
is
is
it the excellent
40.
question?
Okay, you have 4 horizontal here. This is 40. Okay?
Yeah.
And about this, this is precisely the next slide.
Sorry.
So first of all, the thousands and the tens observing each other. They are thousands and tens are in the same direction. The tens of thousands and hundreds conforming with each other. So you have this alternation. And the question you raise is addressed here. For 6, you do not accumulate, whereas for 5, you do not use a row alone. So here you can see 5 for 50, 5 horizontal rods for 50. So 5, you do not use a single rod. Whereas here, to the right of this 5, you do not accumulate, so you have 1 rod for 5 and a single rod for the additional unit. And here, what we are referring to, 1 rod for 5 and 4 horizontal, so this makes 9. So you see in which respect these texts fit with what we see in this later documents. So what we see here is that we have positions that are used to write numbers using calculating rods, but there is more. Indeed, after having described the way of using calculating rods to write numbers, in mathematical canon by Master Sun, we have algorithms for multiplying and dividing. And I would like to draw your attention to this term true for dividing that will recur later. But first of all, I'm going to take you through multiplication to make you enter into the computing technology. So in any multiplication, one puts again the term positions twice, the term positions, and here we have reference to an upper and lower rows observing each other, so the digits are written with comparable with each other, as was the case for instance, thousands and tens. So we have now new types of positions, and we will see they are referred to as position, the upper position and the lower position in order to carry out the multiplication. These positions are meant for the execution of the operation, but what I'm interested in here is the diagrammatization of the computation. And I would like to take you through elements of this diagrammatization of computation. I want to emphasize the fact that I have illustrated here what happens here, but this is my example for you to understand, and this does not feature in the text. So, if, says the text, in the upper position, and here you have the upper position, there are tens, as is the case here, we make the number below move forward to the tens. So, first key element, the fact that the rods are moved, and here we have a motion moving forward, which corresponds to a multiplication by 10. So the text expresses this motion with 3 examples. If there are tens, move to the 10. If there are hundreds, move forward to the hundreds. If there are thousands, move forward. So you move the multiplier down there to the position of the highest position, to the highest power of 10 here. So simply the fact that moving to the left corresponds to multiplying by 10 shows that this arithmetic is decimal, and also that this arithmetic is placed then. And we already have an element of the literacy, which is the ability to write the prescription or to execute the prescription of moving forward. As you can see, the positions of the numbers that are put already serve as reference point to carry out the motion. So the fact that we have inscribed these digits makes position references for the motion of other numbers. We will see this element also later. What will happen here is that we take a digit in the upper row and we multiply it by the lower row in its position. So this lower row, the 23, has been multiplied by 10, and we're going to multiply it by 5. The numbers obtained being in the middle. And here there is a very interesting sentence. If we say 10, we go beyond. So when we say 5 times 2, 10, we say 10, and the 1 is to be put beyond the column, the 10. So you see another way in which the inscription of the numbers serves as a reference point in this diagrammatic way of computing. The same thing if we say 5 times 3. In Chinese, when we say 10, 5, we say 10, and hence 1 is written on top of the 3 in the middle row to the left of the 3. And if one does not say 10, then the number remains. So again, with this go beyond, we have another element of the diagrammatization of the computation. And I want to draw also your attention to another feature of this text, where you see that the lower position will refer to the number in the lower position, whatever it is, which means that we have an assignment of variables. What the lower position means is the number, even though it may have changed. So these positions play the part of memories, if you want, and when you pick up the memory, you pick up the number that was placed there last. Finally, when digits in the upper position have been used, they are deleted, and the 23 is then moved backwards in relation to the next digit to be dealt with. And you see again this term moving backwards, which belongs to an arithmetic that is diagrammatic, and an arithmetic for which motions have meanings with respect to the decimal place value notation. These are all elements of the literacy that these texts require to be used. So here is the overall picture of the multiplication. What I want to emphasize is that in addition to words, in the computing technology, we have positions. And these positions will play a key role. We have seen how the algorithm relied on place value decimal position, with positions referred to as position. We have seen how the algorithm relied on the upper, middle, lower position. For us, these are two different kinds of position, but this is a single term in Chinese. And hence we have the execution that is mainly working with positions. Okay, what I would like to show now is that this way of writing a flow of computation is linked to a key feature of the practice of computing and a key feature of the work with algorithms. And hence, I will turn to other features of the literacy. I'm sorry, it's really here. I'm going to do a little bit of striptease. Because it's really warm here. Aspects of the literacy and uses of the computing technology. So, after multiplication, we have division. And the key point is that the algorithm of division starts not with a prescription, but with an assertion. And I remind you of the fact that we are at the beginning of the curriculum, and hence we are at the moment when elements of literacy are taught to students. I think that this first statement, any division through method is exactly the opposite of the multiplication charm. I think that naturally we need to interpret it, but I think that it refers to a key element of the literacy that was taught at the beginning of the curriculum. Hence, I'm going to work a bit to interpret this sentence. I would like to emphasize the fact that the division here is referred to by the famous term true that I have pointed out earlier. So the meaning of this opening statement is some light is shed on it by the sentence that comes after. The result of multiplication is in the middle. We have seen that the product occurred in the middle row, and the operation of multiplication is completed when the upper row has been emptied. In fact, the result of division, the quotient, will feature in the upper row, whereas the dividend that will be placed in the middle will have vanished. So already from this sentence, you see the insistence that the middle row and the upper row are the two rows in which things are obtained in the multiplication, in the division. But you see, this is in fact a famous pair of opposed characters. What is yielded, what is lost. What is lost is here in the upper row, whereas what is lost is in the middle. So you already have on top two pairs of rows whose behavior are opposed to each other, whereas in the lower row you have the operator that will play the same parts. So let me take you through division by simply emphasizing some features. Again, I don't want to dwell on this, but again, you see here the text is formulated with respect to a paradigm, 100 divided by 6. Dividing 100 by 6, one must move this 6 by two columns, column another term in the diagrammatization of the computation, and again these motions that are used in the computation, so that it's just below the 100. So here, in relation with the paradigm, it's interesting that the text uses elements of the semantic. The semantic of this one is 100, and the text refers both to positions and to the meaning of these positions. Again, without entering into the detail, this 6 is greater than 1, so 1 moves it backward. Again, positions used. And note that in this case, interestingly enough, in contrast to the case with division, with a multiplication, note that now terms are introduced for the terms of the operation, which was not the case before. We did not have multiplier and multiplier. We have divisor and dividend in this text. I will not get into the detail. I don't want to dwell too much on it. But what is really important is this description of the algorithm with respect to positions and using motions in addition to multiplying digits with respect to each other. And so this gives us sequence of operation, at the end of which we have the quotient on top with a remainder for the dividend, which is read as integer plus numerator over denominator. So, with what we have seen, and then we quick on division, we see that mathematical canon by Master of Certain contain texts for algorithm that describe positions, upper, middle, lower, tens, hundreds, and describes in position motion of numbers, operations, deletion of digits, positioning of digits. So we have a mixture that a mixture of type of operations that makes me use the expression of diagrammatization of computation. So these are features of computing technology. These are features of the mathematical culture in which this computing technology is used. And all these canonical texts attest to this culture. And I will show you now that several texts can be interpreted with respect to this background. Because the key point is we have seen, for those online, we should use the mouse instead of the pointer. So we have seen that here is the beginning of multiplication, which ends by the beginning of division. And division ends with the beginning of multiplication. So we have properties of this diagrammatization of the computation. We have properties of reciprocity. But we also have the fact that was emphasized by what is obtained in the multiplication is in the middle, whereas what is obtained is on top. What is lost is on top, what is obtained is in the middle, whereas what is in the lower row, the operator, has the same behavior of being moved leftwards and being moved rightwards. We have here, line by line, two flows of operations that are opposed to each other. And this is how I interpret the first sentence of this algorithm given by mathematical canon of Master Swing. Any division true method is exactly the opposite of the multiplication charm. So I interpret this statement as referring to this fact, which I repeat, refers to the fact that if you look rows by rows, you will see the upper row in the multiplication losing its digits gradually, whereas the upper row in the division gains its digits gradually. The middle row in the multiplication starts from empty and becomes full, whereas the middle row in the division starts from full and ends with empty or sometimes lower than the divisor. And the lower columns in both cases play the same part. The operator plays the same part. So we have a way, through the flows of computation, we have a way of grasping the relationship of opposition between two operations. And what I would like to emphasize now is the relationship between this computing technology, the use of this computing technology, and the knowledge acquired. Indeed, we have exactly the same practice with the calculating surface for square root extraction and cube root extraction. We will have a use of positions, both in the decimal representation and upper, middle, lower, and a use of related transformation and motions in flows of computation. And this holds true for these four canons that I have listed here. So I will illustrate this briefly with the text of the square root extraction. This is the text of the square root extraction that we find in the 9 chapters. I have highlighted all the terms that relate to the description of division. And hence, you see how the text shapes the square root extraction as a kind of division. On the computing surface, this is the division to the left, this is the root extraction to the right. We have to begin with the number whose root is to be extracted, which is placed as dividend, and the divisor will be computed progressively, but playing the part of divisor. You see, it starts to the right, it moves to the left, and it will be progressively taken backwards. So we have the same kind of shaping of the flow of computation and shaping this flow of computation in parallel with that of a division. So in the same way as the flows were expressing the relation of opposition between multiplication and division, we have flows expressing the relation of similarity between square root extraction and division, which is confirmed by the way in which the operation of square root extraction is prescribed, dividing by, if you want to translate it literally, you can say opening the square or detaching the side of the square, or an extraction of the square root, which is the corresponding technical term. So you have to begin with flows of operation that shape a relation of opposition, or that explain the relation of opposition between multiplication and division. And now you have an additional operation that is shaped as a division and prescribed as if it were, and it is, a species of the division. If I return to the text of the root expression, I have put two terms in blue here. One multiplies, because I'm not interested in the details, once, and you can see below, one multiplies it once. It's very strange to make precise that one carries out a multiplication once, but this becomes clear if we look at the cube root extraction. First of all, again, I have highlighted the terms that the algorithm of cube root extraction borrows from the division. Again, the cube root extraction is shaped as a flow of computation as a division, but where we had multiplied once, in the corresponding text we have borrowed multiplied twice. Okay, so the once can be understood only because it is a reference to another operation, and you can see again the shaping of another operation as a kind of division parallel to the first operation. So, to summarize what we have got so far, we have a division whose terms are dividend and divisor, which is prescribed as true divided, and two roots extraction that are prescribed both with true divided and that have the operand called dividend, while the algorithm executing the operation have divisor and quotient. So we see for the shaping of this first kind of architecture of operation the key part played by position, because position are that with which the flows are made to correspond to each other. But there is more. Indeed, in the 9 chapters, as well as in the mathematical canon, the master sermon, as well as the master canon, we have systems of linear equations. And the algorithm given to solve these systems of linear equation first describes a positioning of the data related to the system. So the first equation will be placed in the row to the right. The second equation will be placed to the row in the middle. The third will be placed. So again, here, as we had with division, multiplication, root extraction, whether it be square or cube, again, we have a system of positions on the basis of which the algorithm will develop. So I have expressed this in general terms, since we have systems of linear equation with many unknowns, and the algorithm basically amounts to a Gaussian elimination method. But this is not mainly the point I'm interested in. What I'm interested in is that the row of constant terms is referred to as a row of dividends, whereas the square on top of this row of constant terms is referred with a term which is a synonym of divisor, and I interpret as divisor. But what is mostly interesting is that the elimination between two columns, so this column is used to create a zero here. It is described as an upright division. So again, this operation, some links are built between the division true and this other operation that operates on system of position. So to my table here, I add another paragraph in which we have linear equations that are also somehow related with division. And in fact, I will not get into this at all, but we have another operation, quadratic equation, which derives from square root extraction and which is also shaped as a subspecies of the species of square root. And so what I want to draw your attention to is that we have a body of knowledge with respect to operations. We have a body of knowledge that is built on the operation of division true. Okay, this is the key conclusion that I want to draw in relation to the fact that we have a computing technology with position, in relation to the fact that this computing technology is used in a given practice of looking at relationship between operations. We have what I consider as an architecture of operations that is built upon the division tree. So we have a theoretical work that has been carried out and to which the 9 chapters, the first century canon, attest. So what we see then is that the uses of calculating work, of position, of motions, the computing technology is related to a body of knowledge namely a reflection on operations and on the relationship between operations. Now, what I want to turn to now is to the fact that there is a mutation in the computing technology between the earlier manuscripts and the canonical texts. Indeed, what I would like to emphasize is that we see a discontinuity in the use of the calculating words, and in relation with it, a discontinuity in mathematical knowledge and practice. So the first element is that in all the early imperial manuscripts, never a multiplication by 10 or a division by 10 is carried out by a motion. We will never find moving forward, moving back. Instead, what we have are prescriptions like 1 tenfolds or 1 divides by 10, literally 10 then 1, which is one of the technical expressions to refer to divide. And so, to begin with, I see no hint that the early manuscripts show any evidence of place value notation, despite the fact that they are using calculating words. So for me, there is a discontinuity in the use of calculating words. And because of this, I will play the game of not using Arabic numerals when I show you division from the manuscript, but I will use, even though I could use anything because I don't know how words were used, but I will use Roman numerals. You will see shortly. Okay. But what is really interesting for me is that in relation to the fact that we never have any moving forward, any moving backward, we will see that we never have any system of position that is described. So in relation to the fact that there are no motions, there are no systems of positions used, and this is where I claim that the computing technology has changed. And what I would like to show you now is that in correlation with this first fact that there is no moving forward, moving backward, the manuscript attests to a very different execution of division. So I will show this to you by quoting the last part of this text. Okay, so this text is carrying out sharing into unequal parts. So to carry out this sharing into unequal parts, it makes the sum of numbers representing the size of the parts, and it takes this as divisor, and it multiplies the numbers defining the size of the parts by what is to be shared. We don't mind. What we want to see is that we take the divisor, which is here 62, and we will take the larger of all the dividend. I will take 160, and I will follow what the text describes as division. I will follow it on this example. So I warn you that I have used positions without any meanings for you to see, because we have absolutely no indication of where numbers would be placed, where rods would be placed. I've placed dividend in the middle, divisor below, quotient on top, but this has no meaning whatsoever. It's just for you to understand. So this is what the text begins saying. in the dividends, because the text is carrying out 5 divisions in parallel, just look at one. What is like the divisor? So you have the dividend. In the dividend, what is like the divisor yields a churn. Churn is a measurement unit for length. I should have drawn your attention to the fact that we will have in this text churn and churn, and one churn will be 10. This is all we need to know. It's a decimal system of measurement unit for length. Okay. So what is like the divisor yields one churn. So I assume that there is a first subtraction of the divisor, the dividend by the divisor from the divisor, which yields one churn. A second subtraction, which yields a second churn, and there remain 36 churn. The text, which is smaller than 62, the text goes on. Interestingly, what does not fill up the churn? So it considers that the dividend is filling up the pattern that the divisor constitutes to make a unit of the quotient. So we have something in the dividend that does not fill up the divisor. What does not fill up the churn? 1/10 that. So basically, we have remaining. And I think I need a typo. We have remaining. Where am I? Yes. It should be, I'm sorry, there is a mistake here. No. Yes, there is a mistake. I'm sorry, I made a mistake, which is the following. This is because I wanted to use Roman numeral. So here we have 36 churn. And we want, okay, we have 36 churn, but this does not fill the divisor. So what we are going to do is that we are going to transform them into churn to get the number of churn in the result. So the first remark I need to make is that you see that we obtain the quotient not digit by digit, but measurement unit by measurement unit. Another clue that we do not have a place value notation behind this division. And what is important is that we have text in mathematics where we have division of this kind for weight, for which we do not have a decimal system of units, and it's the same. We obtain the quotient measurement unit by measurement unit. So, contrary to what I have written, so we have 36 churn, and we are going to multiply by 10 to transform this 36 churn into churn to determine how many churn we have in the quotient. So, what there should be here what there should be here is we have 36, in fact, I don't know what I did, but it should be 36 churn multiplied by 10 gives 360 churn, and then we are going to subtract the divisor regularly progressively from the dividend. So the text tells us what is like the divisor 1/3. So what in the dividend is like the divisor 1/3? One subtract the divisor, one obtain 1/3. A second time the divisor, a second third. And in the end, one remains with the fact that one has 5 churn, and that remainder smaller than the divisor. And the rest is given as fractions. So fundamentally, if I summarize what we have seen of this division. The quotient, as I have emphasized, is yielded as components on subsequent measurement units, not as digits. And we have seen that the dividend is a measured quantity that is diminished when there's subtraction and multiplied when we change the units. Whereas the divisor does not change, and in particular does not move. So there is no mention of position, neither horizontal nor vertical, no mention of leftwards and rightwards motion, and multiplying by 10. You have seen here, despite the fact that I made the writing mistake, when one multiplies by 10, one tenfolds the dividend. One does not move the dividend, okay? So this tenfolding is carried out without a motion. So if we compare the division between the earlier manuscript to the left and the canonical text to the right, we see that with respect to the quotient, in the manuscripts, it is yielded measurement unit by measurement units. In the canonical text, digit by digit. In the earlier manuscript, the dividend alternatively decreases and is multiplied, whereas it's only decreasing in the other division. The divisor in the earlier manuscript doesn't change, whereas in the canonical text, it is shifted, and there is no positioning of the two. What is interesting is that the change in the algorithm executing division between the manuscripts, the change in the algorithm is correlated with a change in the terminology that I'm not going to examine more closely, but in the manuscripts, we have true, but true is only used for subtraction or repeated subtraction, whereas you have seen that in the canonical text, true is the pillar of the construction of the system of operation. So I will skip proving to you the change of meaning of the term true, but what I want to say is that in correlation with this fact, we have no system of position, no motion, no hint of a diagrammatic practice of computation. In the early manuscript, from the point of view of mathematical knowledge, we have no hint of an interest in relationships between operations. So, my claim is that we have three correlated phenomena. One is a mutation in the computing technology. And by this, I mean not only the calculating rods, but I mean the use of position, of systems of position, of motions that we see in the later text, and the disappearance of table of multiplication between smaller power of 10. 10 multiplied by 10, 100 multiplied by 100, and so on, in the canon, whereas they are present in the manuscripts. In relation to this mutation in computing technology, we have a mutation of the work with algorithms, where in the canon we have seen an interest in the relationship between different operations that relates to the way in which flows of computation execute these operations. And finally, we have a mutation in the mathematical knowledge produced, where they have shown as the architecture of operations that we find in the canon. So this is my contribution to the theme of the relationship between computing technologies and the practice of mathematics, because I think we have here a very interesting case of a mutation in the computing technology that is correlated with a mutation in practice that is itself correlated with a kind of mathematical knowledge that is very specific. Thank you very much.
So now we have some time. Thank you, Karin. So now we have some time for questions. No?
I can't say I followed every detail of that, but
Sorry.
no, that's a comment on me.
No, that's a comment on.
But one of the things, going back to where this occurred, you talked at the beginning about this being a sort of an educational system for people passing exams. And do you have a sense how much of this was only, so to speak, to pass the exam, a performance to pass the exam, and how much of it was actually being used in practical examples where people might need what we would now call Gaussian elimination?
Okay, thank you very much for this question because it's a very important question. In fact, thanks to the work of the young Chinese family, we have now uncovered a corpus of texts that shows that people are computing in a completely different way, without forms, without visual notation, and by discursive means, by reasoning, in other schools that were studying Confucian canon. So, in fact, in the same time as there was School of Mathematics, there were schools in which Confucian canons were taught, and in the sub-commentaries, the 7th century sub-commentaries on these canons, there is a completely different culture of computation. So, from what I see, we have not understood well enough who was using the place value decimal system, who was using positions, who was working with these objects, but my hunch is it may very well have been experts in mathematics, experts trained with these kind of methods, but certainly not everybody in the society. Certainly not, now that we know that we have a very important corpus of texts in which computations were carried out completely differently. But since I wanted to focus on computing technology and the relationship with mathematical knowledge, I chose to focus on these texts. But it's also very interesting to see how people were computing when they were computing through reasoning and with no tooling.
Yeah, there was a question there.
In connection to what you just discussed, I was wondering if you could say a bit more about the geography of those corpus. So first of all, where is there a place where most of those manuscripts are found? Do you have a sense if there's a difference in computing practices, let's say in a court in Beijing compared to a city like Xi'an, where the connections with the early world or the young world might be more intense?
So most of the texts were found around Hunan. So most of the texts are found in a very specific. But what does that mean? That means that excavations were made there. Most of the texts that we have mentioned. Moreover, as you have seen, we have very little, a very small set of manuscripts. Already, 2 of them were bought on the antiquities market. So for the moment, I wouldn't dare. It's coming here. For the moment, I wouldn't dare. So we have tables of multiplication from the northwest of China, because we have a desert and things are dry enough for some documents to have been preserved from this time period, and otherwise it's more or less Human, plus the antiquities market. But I wish we could be.
Yeah, I was wondering, when they do these calculations, I've noticed that I mean, you say they are, that division is such a central thing, but in the end, I mean, in the calculation, they usually postpones the division, as far as I've understood, until the end. Can they write fractions on the board, or is that why they usually postpone the divisions until the very end?
So what happens is this: in the same way, perhaps I should stay here. In the same way, as we have here, we have calculating rules.
Yeah.
And in the text, we would have characters. In the same way, here we have what is taken as numerator, what is taken as denominator simplified, which in the text would correspond to the way in which in the Chinese language you put a fraction. So there is the fraction on the surface on which you can choose, and there is the fraction in the text. And in fact, depending on which operation we are carrying out on fractions, the layout could change. The fraction could be written horizontally or vertically, depending on the operation. Because we have texts that describe the way in which fractions are laid out.
This is not really a question. This is something that started in my brain, and maybe you can help me structure it. That's really weird. So I get the feeling that it is very much related to a shift between a number in, I'm going to say, an absolute position to an object, because I don't want to say a number because we talked about divisors or dividend or that is seen in relation. So this position seems to change, like in the beginning, it's just how you place something, and later on, position means something in relation to another thing. Did I understand that correctly?
So, frankly speaking, your question relates to something which is very delicate, because I have not seen any absolute evidence that using clues, someone has established for sure that the surface on which computing is happening had cells and hence had positions versus had no cells and no marked position.
Okay.
So I've tried to address this issue by looking at how the term position is used, because in fact the term position can mean, for instance, the position in a sequence that writes a number, but it can also mean the digit. So I've tried very hard to work with all the sentences in which this term occurs to determine through clues what the surface on which people place things looked like, whether it had absolute or not.
Yeah.
Yes. So I think my hunch is that it didn't come. And one of my reasons for this is something on which I've not spoken. At the beginning of the square root extraction, you put 1 in the units, and then you make one motion, jumping a column, a second motion, jumping a column. So in the same way as the divisor moves forward, this thing, which will become the divisor, moves forward. The number of motion counts the number of digits, but you count motion jumping one column. Now, The reason why this one is put there may very well be that you need to know where the units are when you do root extraction. It may be. I'm not sure. It may be. So you see, these are clues like this that we need to weave together to determine what the surface looked like. Because we have absolutely nothing that says something about the surface. I mean, whether it had markings or whether it was completely
Free.
free.
Yeah.
Yes. But I've tried to approach this question from many different angles. One thing I could say is the following, I have not dwelt on it. To my knowledge, these rods, to begin with, were only used for multiplication and division, not for addition, not for subtraction. These operations, it doesn't matter if you multiply 1 by 3 or 100 by 300. What matters is the real thing, and then you adjust the order of magnitude. So this is something else that enters into consideration. So you see, there are many clues that needs to be put together to see what we cannot see.
Yeah, thank you very much for the great talk. I want to come back to the remark you made with respect to the fact that there are words for divisor and dividend, but not multiplier. And I want to know if you have any guess about that asymmetry, and in particular, if there's something that could be connected to either commutativity of multiplication and non-commutativity of division, or the fact that division is not defined all the time. And on top of that, is there any hint on the fact that multiplication is commutative, because the algorithm of the computation is not? You have the upper and the lower, and they are not the same. It's kind of surprising that if you just multiply the terms in the other way, they give this result. So is there something related to?
So, multiplication is commutative for you.
Yeah, exactly. That's the question.
Well, but what I want to say is that as soon, sorry, I pressed the wrong button. As soon as you have put your numbers, one is the operator, one is the operator. So there is a rupture in the symmetry as soon as you have put the numbers on the board. And you have seen that the operator shifts without changing, whereas the operand increases or decreases without shifting. As you have seen in my video, there was the division 2 was the pillar on the basis of which really an important reflection took place on the relationship between operations. So this is my guess for understanding why we have terms referring to the operands for division and not for multiplication. Now, there is something very interesting. Much later, terms were introduced for the operands of multiplication. And these terms were, I will first translate them and then I will explain what that means. So for multiplication, much later, terms were introduced and they were dividend and divisor. And this means that these two terms had shifted their meaning and they meant the operand and the operator. So there was a shift later of these two terms, and this is also true in Japanese texts that use these two terms. The text using these two terms as meaning operand and operator, which is really interesting because precisely you see a reflection on the operation there, meaning that you have something that operates and something on which you operate. So there is a reflection on operation that I find really important to dig out of this text.
I was checking my emails because I told Xenia that she could ask questions.
And perhaps other people also.
I'm not on the Zoom system, so should I check? Because I thought, right, they would be streaming today and not.
You don't have.
But I'm not sure if that also.
I have my slides here.
Yeah, I'm just curious about the operand and operands that these are this explanation. Can you show us the words in Chinese and the relationship with Japanese? And
Who is able to, will be because I clicked.
Oh, okay.
Who knows how to put me back? Who knows how to put me back on
I think,
front
So-
screen?
Maybe.
Console.
yeah,
Thank you. So you want the term for,
these terms and I mean, I was interested in the relationship with Japanese.
So Karine and Elizabeth,
So here.
sorry to interrupt. So apparently they are quite strict about the fact that we need to close the building, or they will close the building, so we should actually, you can, I'm very sorry, so, but we should stop here. I know there were
Okay.
other
No, we
questions,
can talk about this another time.
but there is a reception that was organized
Sorry for
by
the-
Ursula, and so we can
We
continue.
can talk about this.
Yeah.
Anytime.
well, we should.
Yes, so we thank.